Hello, and so we're going to try to prove the angle bisector length formula, which is something we sometimes actually love using it. So one of the things that we kind of need to know is angle bisector theorem itself, which is I'm not going to go around this video because I had that in the other videos anyway. So if you need to look at that one, so I'm going to put into description as well. So, but one thing is we kind of need to know is angle bisector theorem. But now we are going to find the length of the angle bisectors. Okay, so to see how that looks like. But what we want is a triangle. But whenever you have a triangle, you can always put into a circle. Okay, so which we call circumscribed circle. So let's take a triangle of our choice. I'm gonna make something like this. Again, any triangle you can use. So you can put draw a circle around that triangle. So I'm gonna do it this way. If you are wondering why we are drawing the circle around a triangle in this case, because when you have that, so we have some equals angles that is corresponding, so which will make our similar triangles, right? So which is why I'm gonna show that proof. So this is a triangle, and then let's say our A is split into half, right? So I'm gonna use actually different color. So let's say angle A is split into two equal pieces, and that is the angle bisector. Okay, so far so good. So let's say this is the equal to this angle. So our goal is just to get relation between AB, AC, and then these two pieces. I'm gonna call maybe, I don't know, like this is E. And to do so, my first step would be just extending that line AE. So you will see why we are gonna do that. So if I extend this, it will touch the circle one more time. I'm gonna call that D. And when we do have such a thing, we do need to remember angle, inscribe angle like definition. So the angle right here is facing towards arc BD, this angle facing towards DC. So they are gonna be equal. So let's keep that in mind. But what I'm gonna do, I'm gonna make some triangles. So I'm gonna try to connect these two, which is BD, right? And when we do have these, this angle is facing towards BD, which is good. And this angle facing towards like DC, which is also okay. But now we do have another angle. Let's say this angle, I'm gonna call, let's say blue angle. So this angle faces arc AB. But this, if you look at BC and AC as the two chords, and the angle in between those two is also facing towards the same arc AB, which is why this angle and this angle must be equal, which is a definition of the inscribed angle. Okay, that's good. But also another way we can see, ABD has this angle and this angle, but at the same time, AEC is also have the same angles, which means they are similar. So let me write that as well. So the third angle B, I'm going to call this angle, has to be same as this angle. Why? Because these two add up to whatever number. When you subtract from 180, you got something. But in this triangle, this angle plus this angle is the same as some of these two, so which means the third angle right here should be the same as this guy. So with that in mind, so let's write the ratio. So I mean the similarity. So the AEC, so this is my triangle, is similar to, okay, ABD, but I start with A. So in this case, so I should use the same angle, which is A as well. So the A, and then E was the second angle, so it has to be B. So the B and D. And the reason is angle-angle similarity. Okay, so let's write the ratio, but keep that in mind. We just don't really care about BD and DE. We just need to relate the AB, AC, BE, EC, and AE. Those are the part of the actual triangle. So with that in mind, so let's write everything first. So this blue angle opposite to AB, in the first triangle AB, the blue angle is opposite to AE, equals, in this triangle, let's say this angle opposite to AD, the same angle right here is opposite to AC, equals, in this triangle, this angle opposite to BD, the same angle right here is opposite to EC. Okay, so I wrote all three size ratios, but we are not going to use all three, so we'll see which one we actually need. Okay, but at the same time, this is just one pair of triangles. We also have another pair right here. So BED, this triangle, and this triangle are also similar because this angle and the opposite right here is also congruent because they are vertical angles. So which means this blue angle and this angle is the common to these two. And then that means the third angle right here has to be the same as this one. And now we have seen why that's the case, because this angle is opposite the arc DC, but this angle is also opposite that same arc. So which is why we actually can say this part of the angle B is the same as this angle. So let's write that ratio as well. I mean, the similarity statements as well. So then I'll say BED, the triangle BED is similar to, so I start with B. So the same angle right here is A. And then E is the same as E, so that's AE. And then D is the same as C, so that should be AEC. And the reason is still angle because they have same angles. Okay, so let's write the ratio. In this triangle, angle D is opposite to BE. And this angle C is opposite to AE. Okay, equals, and this triangle, angle like E is opposite to BD. And then angle E is opposite to AC. And then in this triangle, this angle opposite to DE, and the same angle, which is this guy opposite EC. Okay, so now we kind of want to use these two to get some relation, but we just need to keep in mind, we are trying to relate AB, AC, AE, BE, and EC. Those are my part of the actual triangle that we saw it. Okay, so with that in mind, AB and AE, so in this first equation, this fraction is both of these segments is part of my actual triangle, which is kind of important. And AD is the entire thing. AC is what we are interested. So maybe I can use still AD, but I don't want DE. Maybe I can write like AD as, AE as AD minus DE. So that might be useful. And then BD and EC, BD is right here, EC right here. So I can try using relating those as well. Let me use this guy. So the first two. And in the second case, I have BE and AE. So BE and AE. So both of them are actually part of the actual triangle we saw with. So that might be useful. And then BD and AC. So again, BD is good, but I like to kind of write maybe AD as some of the AE and ED. So maybe I can take the AD and subtract from AD. So that's why I kind of have AD right here. So maybe I should use something like this, right? So maybe DE. So I'm going to take this one instead of this one. I'm going to write DE as, I'm going to take the DE out of AD to get AE. So let's see if that's going to be useful. So with that in mind, so maybe first take this fraction and multiply crossly. So BE times EC. So you get BE times EC equals AE times DE. So what I just did, I just ignore this middle part, and then this equal to this one, I just cross multiply to get this relation. And similarly with this guy, so if I do cross multiplication, so you will get AB times AC equals AE times AD. So this looks like D. Okay, but the question is, I like to get AE. So we have AE right here, AE right here. It looks like we have the same AEs. We can kind of add or subtract. And then DE and AD. So this is AD, which is the entire distance, but I like to AE, not AD. Maybe I can subtract this equation from the first equation. So let me write here. So the AB times AC equals AE times AD, and BE times EC equals AE times DE. So I'm going to subtract the second equation from the first one because I'll take the DE out of AD, and then we have nicely AE is common factor. So that should be like AE times AD minus DE. Again, if this doesn't make sense, so write this as a difference and pull the AE as a factor. So you should get in this one. And then we got AB times AC minus BE times EC. Okay, so then AD minus DE, AD is the entire segment, and then DE is this segment. So when you take that, so you got AE. So which means this parenthesis is actually the same as AE. So you will get AE times AE. And then the left side AB is the part of the original triangle. AC is part of the original triangle, minus BE, and EC is also. So which means we actually are done with the proof. So AC minus BE times EC. So this is called angle bisector length formula, but it looks like a bit fancy looking, right? So, but it is actually not that bad. So basically, you have angle A is split into half by AE. The square of that, AE squared, is equal to the two sides next to the angles, AB times AC. You multiply those and subtract the product of the BE and EC. So it's a quick example of kind of line this. Let me try something like this. Let's say we have a triangle, and I will say this is maybe angle bisector. Okay, so this angle and then this angle is equal. So let's say this is 5, this is 6, and let's say this is 7, this third side. So like if this is the question, and if I ask you to tell me what is this distance, you just need to know this piece and this piece, which we do not know, right? So there are different ways you can do this problem, but let's try to use this new rule or relation. But to use this one, I need to know this segment and this segment, which is why I kind of need to know the angle bisector theorem itself. So angle bisector was telling us when you split the angle you have, these 5 and 6 actually proportionally divide the other side as well. So which means this is 5x and this is 7x. So if I say this is 5x and this is going to be 6x, added up to 11x equals 7. So the x will be 7 over 11. And then that means 5 times x will be just 35 over 11. And then 6 times will be 42 over 11. As soon as you have those, then I'm going to call this, let's say x. AE times AE, which is the angle bisector squared, is equal to 5 times 6 minus 35 over 11 times 42 over 11. And then that will be our equation to solve for. So again, the numbers are not nice because I chose that way, so you can actually not get it immediately by using some other approaches. So when you simplify the right side, so you get 30 minus a product, you can try to simplify like 7 times 5 times 6. You can kind of pull that 7 outside after you subtract stuff, but I'm going to leave that for you to finish up the problem to get x alone. So, and then as soon as you simplify and take square root, so you got the x, which will be your answer. By using the angle bisector length formula, this is actually going to be a quite easy problem. But here's my challenge for you. First, solve this equation for x and tell me what number you get. You can write in the comments if you like. And then try to do this problem, maybe using different approaches, not angle bisector line formula. So try to use something else. If you know the, I don't know, like Stewart, or you can maybe use Harris formula, or maybe use Pythagorean, or any other approach you like to use, and kind of tell me which one is easier. So which one do you prefer, especially with these numbers, 6, 5, and 7. Okay, so and then share with me in the comments. I'll see you in the next video.